Hi, and welcome to my talk. First of all, I would like to thank the organizers for giving me the opportunity to present my work here. I'm Lisa Wölfer, and I will now talk about a highly non-Keplerian protoplanetary disk, the CQ-Tau disk, where we find spiral structure in the gas. Now, in the past few years, high angular resolution observations have shown that protoplanetary disks appear in a variety of shapes, showing rings, gaps, spiral arms, and azimuthal symmetries. And this has given rise to the questions of what is formally substructures, how common they are, and if there might be signatures of planet formation. So now the big question is, how can we determine whether these substructures are indeed due to planets or other mechanisms? One thing we can do, we can directly image embedded planets like it was done for the PDS-70 system. However, this method is only feasible for very few and very massive objects. So to increase the database, we can also look for the indirect effects that might be induced by planets. For example, a planet can carve a very deep dust and gas cavity into a disk. Also, we can look for spiral structures that might be dynamically launched by a companion. On top of that, we can study deviations from Keplerian motion. We can either look at velocity kinks, so very localized perturbations in the channel maps. We can also have a look at the gas rotation and distinguish deviations from a Keplerian model, and then use these deviations to characterize the shape of the perturbation. Here I will present data from the CQ-Tau system. This includes intermediate mass star located at a distance of about 162 parsecs. The system is about 10 million years old and shows an inclination of 35 degrees. And the star was found to be surrounded by a very massive transitional disk that is imaged here in the 1.3 millimeter dust. And here the authors found that there's a deep dust cavity at 53 AU, a deep gas cavity also at 20 AU, and they proposed a massive planet inside of 20 AU to account for this structure. The disk was also observed in small dust grains in the near-infrared scattered light. Here a small spiral structure was found. The authors here performed a logarithmic fit for the structure, which returned a large pitch angle of 34 degrees, and also they proposed a massive planet as a possible cause. I will present band 6 ALMA data from cycles 2, 4, and 5 of these 3 CO isotopologues imaged at resolution of 0.1 arcseconds. So let's first have a look at the channel maps, because if there is a planet present, we would hope to find signatures of this planet in the channel maps. These here are the channel maps for 12 CO, and unfortunately we didn't find any clear kinks, but also our spectral resolution is not very high. So in order to trace the imprints of a planet in the channel maps, we would probably need much higher resolution. From the channel maps, we can construct intensity maps, and I'm showing here the peak intensity maps for all 3 CO isotopologues. We converted to brightness temperature with the Planck law. First of all, we clearly see that there's a gas cavity present. On top of that, we found some underbrightness along the minor axis. And here we have to be careful because this can be a beam dilution effect. And we tested for this with some synthetic image cubes. And indeed, we find that beam dilution can mostly explain the presence of these dips. On top of that, we find that there is some east-west asymmetry. So the east side is brighter in 12 CO, slightly brighter in 13 CO, and then the west side is brighter in C18O. And I would like to note here that here we are mostly tracing temperature, while here we are mostly tracing column, since C18O is more optically thin. From these maps, we can also construct the azimuthally average radial intensity profiles. And this is shown here. For all CO isotopologues and also the continuum. What we see here is that there's the drop of the intensity at the 20 AU gas cavity. We also see the drop of the intensity at the dust cavity. On top of that, we find a slight dip in C18O at 80 AU. So maybe there are some depleted regions. It's also possible that instead we are actually tracing enhancement of emission at 100 AU at the edge of the continuum due to an enhanced desorption of CO ices. So now let's start looking for spirals, and let's start with the gas temperature. In this context, 12 CO, which is optically thick, can be used as a measure of the actual kinetic gas temperature. So we can take the brightness temperature map, then we can subtract the azimuthally average radial profile to enhance substructure. And following this approach, we get these residuals. And what is clear is that 2 spirals are popping up. We have one smaller spiral and then one large spiral here in the brightness temperature residuals. So let's then also have a look at the gas rotation velocity. We used the Bethe moments code to compute that. This fits a quadratic function to the brightest pixel and to neighboring pixels, and then finds the centroid of the line pixel coordinates. And the rotation pattern that we get looks like this, here shown for 12CO and 13CO. And we see that it's striking out that the kinematics are far from Keplerian, and that instead they are twisted and bent. So the blue shift part is bent up, the red shifted part is bent down. We see this also here in 13CO. Now we can analyze this pattern by fitting a Keplerian profile to the rotation map. We used code for that. Here we have the possibility to fit for a thin or thick disk, and we can also include a warp. Sometimes twisted kinematics are linked to misaligned inner disk. So we performed a number of runs here using these different options and fitting different regions of the disk. And what I'm showing now here is the best fit model for a thin disk approach fitting the whole disk. Now we can subtract this model from the data to get the velocity residuals for 12CO, and this looks like this. And what is striking here, that also here some spiral structure pops up, and it's a very large spiral structure covering more than one azimuth. So the kinematics are totally dominated by the spiral structure, which is probably also the reason why none of the thick disk or warped models actually converged. To analyze the spiral structure that we see, we performed by eye fit, and we used two functions to reproduce the morphology of the spirals. First, an Archimedean or linear spiral, and then also modified logarithmic spiral, which worked much better, and therefore I will only show results for this function. So here I'm showing the results from the fitting process. We have here the brightness temperature and here the velocity residuals. Then on the top we have the deprojected and rotated maps using the position, angle, and inclination of the disk. And then here we have the polar deprojected maps in the bottom to show the nature of the spirals. And overlaid are the logarithmic fits, which work very well for the spirals that we observe. Then we can also compare the temperature and velocity spirals by overplotting here the temperature spiral and the velocity map, and we see that they appear to align in outer parts of the disk, but there's a strong deviation in the inner disk regions. Here I'm also showing the location of the near-infrared spiral, and we see that it's located at the anchoring point of the large temperature spiral. From this, we can now calculate the pitch angles or opening angles of the spirals with this function, and I'm showing this here for the logarithmic spiral. In the region where the spirals are present, we can extrapolate this also to the inner disk regions. And as I said, the near-infrared spiral is located at the anchoring point of this large temperature spiral, and we included here the near-infrared spiral, and we see that there's a strong deviation in the pitch angle. So the pitch angle is much larger for the temperature spiral that we find than it is for the near-infrared spiral. Overall, the pitch angles are relatively large and also still far from the star. They appear to be quite large, which is actually a bit puzzling. This was all for 12CO. Now we can also have a look at the optically thin lines, and here I'm showing the residuals now for 13CO. We got them in the same way like for 12CO. And overplotted here is the spiral from 12CO. Now when we look at the temperature residuals, we see that there is also the indication of a spiral here in 13CO, similar to the 12CO spiral, and also the anchoring point is clearly visible in 13CO. For the velocity, we also see that there's indication of a spiral that is, however, slightly more tightly wound. In C18O, we didn't see any features because the signal to noise is not high enough. So now the big question that remains is what is launching these spirals? First of all, we find that there's significant spiral structure over the bulk of the disk in the brightness temperature and in the rotation velocity. And also there's a similar feature in the near-infrared, so we think these are real structures. We find that the spirals are loosely wound, so the pitch angles are relatively large, and this is in general consistent with a massive and balanced planet. It's not the only explanation for spirals. Also gravitational instability can launch spirals. However, the small number of spirals is unlikely for GI. But it's possible that several spirals will only appear as one or two due to resolution effects. What is important to know is that the pitch angle depends on the temperature. So in the passively heated disks and in the planetary scenario, we would expect the pitch angles to increase towards the surface. In the GI scenario, shocks would heat the midplane, and therefore we would expect the pitch angle to be similar for the midplane compared to the surface. So what we will need to really distinguish launching mechanisms is different layers. We already have traces for different layers. However, the observations of the optically thin lines need to be deeper to have a higher signal to noise, and in the continuum so far no spiral structure was found. If the spirals are launched by a companion, we would expect this companion to be located where we have a rapid increase of the pitch angle, since the spirals tend to open up towards a planet. In this case, the planet would be inside of 25 AU, and this is consistent with previous work. As a summary, I would like to show you this sketch. So what do we see in CQ tau? We have a large gas cavity, a large dust cavity. We have spiral structure in the near infrared, the 12 CO, brightness, temperature, and rotation velocity, and we have bent and twisted kinematics. And therefore, all of this might be caused by a massive embedded planet. The inner disk regions are not resolved so far, so we need better observations here in order to constrain the position angle inclination of the inner disk to maybe see if there are some misaligned inner regions. And with this, I would like to thank you very, very much for your attention. If you have further questions, feel free to contact me, and goodbye.